Hi everyone. Today we're going to talk about the evidence that we have behind the Big Bang Theory. So let's get started. So, since the Big Bang Theory states that the universe has been expanding since the beginning of the universe, kind of like a balloon. So, if we thought of the universe as a balloon, then that balloon must have been expanding slowly. That also means that any light that was given off in the beginning of the Big Bang Theory, Big Bang, when the universe was really hot and dense, that light wavelength, the difference between the waves, must have also slowly been expanding. And remember, different wavelengths of light are become different types of light. For instance, if you look at your reference table, page 14, the electromagnetic spectrum, we see different types of electromagnetic waves or light. And our we can only see visible light here, but there's other types of light, right? And depending on the wavelength, whether it's increasing or decreasing, you're seeing a different type of light. For instance, red has a longer wavelength, violet has a shorter wavelength, and if you have a even wavelength that's even shorter than violet, then you can't even see it, but you have a different type of light, such as ultraviolet, X-ray, or gamma rays. Let's write this down. On your reference table, page 14, you'll find the electromagnetic spectrum. So, you're probably familiar with a rainbow. And how a rainbow works is light passes through something that splits the light into its different components, like a rainbow, and the colors of a rainbow. And normally, when we see a rainbow, light is passing through a rain droplet, a water droplet, and being split into its all these different colors. And you'll see that each color of light has a different wavelength. But scientists figured out that if you pass light through a gas first and then split it into its components, that gas will actually absorb some of that light. And when you split it into its components to form a rainbow, then the light that the gas absorbed will look black. So we'll see black lines on the rainbow when you pass light through a gas first. Remember, stars are massive balls of gas, right? So, what we figured out is when light passes through a star and enters the Earth, then that light will also, so that gas from the star will also absorb some of that light from the star. And if we take that star's light and put it into a device called a spectroscope and split it into the colors of the rainbow, we see black lines on the rainbow because the gas from that star absorbs some of that light and causing these black lines. And the thing is, each type of gas will have its unique fingerprint of black lines because each type of gas will absorb different wavelengths of light. And what's really interesting is, say I have a laboratory reference of helium. I tested helium, I passed light through helium, and then split it into the colors of the rainbow. And I see that helium produces this specific fingerprint of black lines on its spectrum. Now, if I compared this helium in my lab to the helium that I see in a nearby star, galaxy, nearby galaxy, distant galaxy, and very distant galaxy, I'm seeing that it's still helium because it's still the same pattern of black lines, but those black lines are starting to shift towards the red side of the spectrum. And why? Because remember, the universe is expanding, right? And as the universe is expanding, the light that came from the beginning of the universe must have also expanded the wavelength between the lights. And we know that different wavelengths of light create different colors of light and types of light, even. So, say, from a very, very distant star, from long, long ago, from the very early universe, there's light that passed through the gas of that star and then reached Earth, right? But it took a while to reach Earth. It took millions and millions and millions of years to reach Earth. And by the time it reached Earth, the universe probably has already expanded. So originally, if say that star was made up of hydrogen and that light passed through hydrogen gas and then it came to our spectroscope, the device that we use, and we split it into components, and then we have a black line and I know that it's hydrogen, right? But if that light from the universe took a while to come to Earth, and it took a while for us to split it into lights because it took a very long time to come to Earth, then by then whatever hydrogen lines that we see, by then those hydrogen lines must have that light that came from that hydrogen from that star must have already, the wavelength of that light must have already expanded. So that means that even though this is what we should be seeing for hydrogen, these black lines right here, by the time the light arrived on Earth, the wavelength must have increased. So for instance, the red's wavelength must have increased, the orange wavelength must have increased to become red, yellow's wavelength must have increased to become orange. This black line used to be green, so we can't see it, but if it was still green, that green's wavelength must have increased to become yellow. Blue's wavelength must have increased to become green, and purple's wavelength must have increased to become blue. The thing is, we can't see this increase in wavelength because we're still seeing a range of a spectrum, right? But we can see what's happening to this black line that was the light that was absorbed by the gas. Before it arrived on Earth, say a gas from a star or a galaxy back then. And this black line would also shift towards the red side if the wavelengths of all of this increase. Because remember, increasing wavelength moves towards the red side more, kind of like this here as well. As purple light's wavelength increase, it becomes blue, and blue's wavelength increase, it becomes green. As green's wavelength increases, it becomes red, and so on. So even though we can't see it, the reason we're seeing, as we're looking far away into the universe, we're seeing these black lines shifting towards the red side is because by the time distant galaxies light came to us, it took many, many, many years. The universe has already expanded, and the wavelength of all those lights have also expanded. That's why it's looking like it's shifting towards the red. We call this redshift of light, and it's called redshift because the light spectrum, the black lines, are moving towards the red side as we're looking far away into the universe, simply because the wavelength of those lights have expanded by the time it entered Earth or reached us, and we've detected them. And remember, it's all the same. Say we're talking about hydrogen in a lab and we're comparing the same hydrogen to other stars and galaxies. It's still the same hydrogen, so we know it's the same exact element, and we know it should look like this, like our lab does. But by the time it reached Earth, the light has already expanded the wavelength, and that's why the black lines look like they're more towards the red side. We call this red shift. And that's our first evidence of the Big Bang Theory, the red shift of light. And it shows us that the universe, everything in the universe is actually moving away from us, meaning the universe is expanding. So if I have a nearby galaxy, that galaxy is also expanding or moving away from us, just with the universe moving, expanding. So, and this shows you that compared to the lab, if something is moving away from us in the universe and we're looking at the light from that, then and we're looking at a certain element compared to our lab, that element's light spectrum or black lines will move towards the red side, and the wavelength of the light is longer. That's what redshift is. Now, what would happen if something was coming closer to us, or the universe was shrinking from this to this? Well, the wavelength of light will become shorter, from red to green to blue to violet. And that means if say from a distant star, the light from the star entered through the star's gases, and then it came to Earth, and we split it into components. Those light spectrum lines and the black lines will shift towards the violet side more, or the blue side, because all of its components or the colors of light would be decreasing in wavelength. So if I'm comparing to the lab, I would see that, say, Barnard star, a specific star, if it was moving closer to us, then the lines would shift more towards the blue side if we're looking at the same element. This is also common sometimes, with more closer objects because of gravity. Say a star is really close to Earth, or something is really close to Earth, it will look like it's moving closer sometimes because of Earth's gravity. Let's write this down. The blue shift of light means the wavelengths of light are becoming shorter, and everything is moving closer to us. So if we're comparing to the lab, then those same lines of that element will move more towards the blue side if the galaxy or the universe was shrinking or things were approaching us. And that's it. Actually, one more thing. How come everything is looking like it's shifting more towards the red side? The farther we are looking out into the universe, the lines are moving more towards the red side. That's because the farther away a celestial object is away from us, the faster it is moving away from us. So very distant galaxies have shifted way far away from us. The universe has expanded much more as it's moving away. And more closer things like nearby stars are taking its time to move away from us. So the more the lines are shifting towards the red, the more those objects have moved, or are moving away from us at a faster rate.